Imagine for a moment, if you will, looking down at Earth from the vantage point of space. Today, we see a vibrant blue planet teeming with life. But if we travel back in time to around 700 million years ago, you would witness a very different sight. A blinding white sphere, encased in ice, known as Snowball Earth. It seems improbable that life could ever flourish in such extreme conditions. Yet recent discoveries suggest that amid the icy expanses, there were small, ice-free oases that provided refuge for our earliest complex ancestors. During a period referred to as the Cryogenian, which spanned from 720 million to 635 million years ago, the Earth was enveloped in massive ice sheets that crept from the poles down to the tropics. Temperatures plummeted to as low as 50 degrees Celsius. The bright white surface of the planet reflected sunlight instead of absorbing it, a phenomenon known as the albedo effect. This reflection kept the Earth trapped in a prolonged state of extreme cold, leading scientists to label this period as Snowball Earth. Traditionally, it was believed that under such thick ice, sometimes a kilometer deep, the connection between the atmosphere and the ocean would be severed, resulting in a muted climate with little variation. But our recent research, published in Earth and Planetary Science Letters, challenges this long-held perspective. We discovered that the climate during this period was unexpectedly dynamic and oscillated in ways strikingly similar to our own climate today. Our pivotal findings emerged from the Garvalach Islands, located off the west coast of Scotland. Here we examined rocks formed during the Sturgeon glaciation, the first of two significant Snowball Earth events. The geological record preserved in these islands serves as an extraordinary archive of this frozen epoch. Among the most revealing are laminated sedimentary rocks, known as varves. Imagine a serene lake where sediment settles quietly over time. Layers build up on the lake bed, creating a natural record that geologists can later analyze to decipher past environmental conditions, including climate changes. In our investigation of a unique 6-meter-thick rock formation on the Garvalach Islands, we identified approximately 2,600 varves. The insights they offered were nothing short of astonishing. Instead of revealing a monotonous, uniform record, as one might expect from a world locked in ice, these layers demonstrated predictable cycles, occurring over years and even centuries. What was particularly surprising was that nearly the entire spectrum of climate rhythms we recognize today was preserved within these ancient sediments, including seasonal variations and phenomena like El Niño, which typically occurs every 2 to 7 years. The implications of finding such cycles in a snowball state are profound, as they suggest a level of interaction between the atmosphere and oceans that was previously deemed impossible under thick ice. So, did parts of the ocean remain ice-free during this frigid epoch? To explore this question, we turn to computer climate simulations. By adjusting the amount of ice covering the oceans, we could observe how surface temperature patterns shifted globally. Our simulations indicated that when the ocean was completely frozen, climate oscillations were largely suppressed. However, even a small fraction of open water, around 15%, was enough to rekindle these oscillations, facilitating interactions between the atmosphere and the ocean. We believe that the sediments we studied likely document a patch of open water in the tropics, sometimes referred to as an oasis. These oases could provide a critical explanation for how life persevered during nearly worldwide glaciation. Interestingly, multiple lines of evidence suggest that such partially ice-free oceans existed around this time. Could our findings indicate that there were temporary warm spells during the Snowball Earth period? While they confirm the existence of transiently warm patches in the surface ocean, it's essential to note that the rocks represent a mere snapshot of about 3,000 years within a much longer glaciation. This moment can be viewed as a fleeting slush ball state in an otherwise frozen world. Recent studies propose that liquid water might persist at temperatures as low as 15 degrees Celsius, provided it is highly saline. What's striking about our analysis is that it indicates a fundamental tendency for the climate system to oscillate, even under the harshest conditions. These ice-free oases may have served as life rafts for early complex organisms. This brings us to a fascinating paradox. The extreme conditions of Snowball Earth may have catalyzed a biological revolution. During this time, the diversity and abundance of multicellular life exploded, an event likely fueled by phosphorus-rich dust churned up by the glaciers that threatened to extinguish it. Scientists believe this flourishing of life occurred during the warm interlude between the two snowball glaciations. Yet, for life to thrive after the ice melted, it first had to withstand the second major glaciation, known as the Marinoan. Our study offers a potential solution to this riddle. If tropical oceans weren't entirely frozen, but instead harbored pockets of open water, these oases could have acted as crucial refuges for life. So, rather than envisioning a planet completely encased in ice, our findings present a more nuanced picture of an oscillating world. In this scenario, thin cracks in the ice or more significant patches of open water created habitats that not only allowed for survival, but encouraged the colonization of life. By maintaining biodiversity during one of Earth's most extreme ice ages, these oases ensured that when the ice finally receded, life was ready to flourish into the complex ecosystems we see today, ultimately leading to our own existence. In conclusion, the story of Snowball Earth is not merely one of ice and desolation, but rather a tale of resilience and adaptation. These ice-free oases offer a glimpse into a world that, against all odds, fostered the very beginnings of life as we know it.